Welcome to the GATE Academy again. So we are here to continue with our series of the new additions into the GATE syllabus 2021. So we are discussing the steam turbine and gas turbine, which is a newly added topic in GATE 2021 syllabus. Okay. So I, Umashankar Tripathi, would like to welcome you back on the GATE Academy English channel. Okay. So first, let me introduce a little bit about myself. So who am I? So as you can see on the screen, our topic which is continuing is steam turbine and gas turbine. Steam turbine and gas turbine. And as you can see, my name is Umashankar Tripathi. Okay, and currently I am a PhD scholar at IIT Roorkee. PhD scholar means you call us research scholar as well. So before entering into this PhD program, I have completed my MTech from IIT Roorkee itself. So after completion of MTech, I joined into this PhD program. Okay. So my MTech, I have completed. This is my MTech year from 2014 to 2016. I have completed my, good morning, Viren. I have completed my MTech. So for getting into this MTech admission, I obviously have qualified the GATE examination. So I did it with I joined IIT Roorkee from my GATE 2014 score. So I had in GATE 2014 65.66 marks with all India rank of 916. Okay. Again, GATE 2015 I gave. So in this, I got 77.02 marks with all India rank of 643. All India rank of 643. Okay. So this is my history of GATE examination. Okay. So just a brief introduction about me because this is the second last session of this series. Okay. This is the second last session of this series. We already have completed 10 sessions. Okay. So if you have not watched those sessions, I would recommend you please go and watch them so that everything will be very much clear to you guys. Okay. So as I said, we are continuing with our lecture series. So we have completed till this session. So before this session, 10 sessions were completed, and to watch them, you must subscribe the GATE Academy. Good morning. GATE Academy English channel. There you can find all these. Okay, so we are going to continue with our today's session. Okay, so we have 2 sessions today, and we will be completing the whole thing within these 2 sessions. Okay, so let us quickly continue and go back to the point. So in the last class, what we have seen, we were discussing about the Brayton cycle. As I told you that in gas turbine, we do not require to again analyze the gas turbines because we already have analyzed the steam turbine. So the same velocity triangle, same degree of reaction, same way of work done, same way of calculations of power, same way of impulse turbine, reaction turbine. So everything is already covered in the steam turbine section. So same you can paste in the case of gas turbine. Okay, Okay. So for gas turbine blading triangles, we are not going to discuss again because we already have discussed the turbine blading. It is exactly almost same to that. Okay, there is reaction turbine, impulse turbine. So we already have discussed in this series what are the differences of those, what are the kind of impulse turbine we have, what are the types of staging we have, what kind of reaction turbine we have. Okay, what kind of nozzle we have, supersonic, subsonic condition, everything is same for the gas turbine. So we are not going to discuss that again. So we are analyzing the cycle of gas turbine. Okay, so we were discussing the ideal gas turbine cycle in the previous class, in the last class. So we were discussing with the Brayton cycle, and in the last class we have seen this was our last class. So in the last class we have seen the intercooling of Brayton cycle. We have seen when we do the intercooling of Brayton cycle, when we do the intercooling of Brayton cycle. In the last class, we have seen those things, that when we do intercooling of Brayton cycle, what happens, what not happen, okay, what happens, what not happen. So in intercooling, what we do, we use our intercooler in between two stages of compression. So we use two compressors, and in between those compressors we use a constant pressure heat rejection device known as intercooler. So this is the intercooling cycle of the Brayton cycle. Let's just quickly revise what we have seen. Okay, so between, you can see we have a compressor 1. So air enters in compressor 1, get compressed, and will go to the intercooler. This is the intercooler. In intercooler, the temperature is reduced on the same pressure. Okay, then again it goes to the second stage compressor, where we again compress it, so its pressure is again increased. After leaving from the second stage compressor, it goes to the combustion chamber, at which heat is added to it. On the constant pressure. Then after combustion chamber, it goes to the turbine, where expansion happens. So we have seen all these things in the previous sessions. This is the TS diagram. What we have made, and these are the observation that while when we do intercooling in Brayton cycle, our net work done increases. How our net work done increases? Because by using intercooling, or by compressing the air in two stages, our work done in the compressor reduces, so the net work done increases. Okay, what else effects we have seen? We have seen by intercooling, the mean temperature of heat addition reduces, the mean temperature of heat rejection also reduces. And what is the overall effect on the efficiency? That the efficiency decreases. Good morning, Trojan. Efficiency decreases. All right. So this is the TS diagram what we have made from it. Okay. You can see from 1 to 2. This is the TS diagram from 1 to 2. We have explained all this. 1 to 2. What is happening? Pressure is increasing at constant entropy. So we are reaching to the next pressure line. Then at the same pressure line, heat rejection takes place. So our entropy decreases, temperature decreases, and we reach to this point of 3. Then from 3 to 4, again compression is happening, and our pressure is increased from 3 to 4, and we reach to this point 4. Okay. Then heat addition happens, and we reach from 4 to 5. Entropy increases, temperature also increases, so we reach to 0.5, and from 5 to 6, isentropic expansion, because we are right now analyzing the ideal conditions. So 5 to 6, isentropic expansion happens, and from 6 to 1, again constant pressure heat rejection happens. Okay, this was the PV diagram, and I have showed you in the last session that how the saving of work takes place. Okay, so from here we are continuing. This is the efficiency formula. When you use intercooling. Okay, so I told you in the last lecture that whenever we have to get the efficiency, we want to get efficiency, you can go for your basic concept. Basic concept is what? That efficiency is net work done upon heat added. Okay, so yesterday we left our discussion, in the last session we left our discussion with this perfect intercooling. So what I told you, what is the meaning of perfect intercooling? So in perfect intercooling, so let us make the TS diagram of intercooling again. So all of you who have not seen the previous session, or who are not live in the previous session and not yet seen the previous video, must be able to understand, this. Okay, so here goes our 3 pressure lines. Okay, so the first step what I gave in the last session, whenever your play is between three pressures, so you first prepare the three pressure lines so as there is no mistake happen while you make the TS diagram. So from 1 to 2, what was happening? From 1 to 2, what was happening? So isentropic compression, so pressure increases. So we go from lower pressure to the intermediate pressure, Then at constant pressure, heat is being rejected. So we reach to this point 3. Then from this 3 point, we go again getting compressed in the next stage of compressor. So our pressure increases, hence temperature increases, and isentropically it is happening. So our entropy remains constant. Then we reach to this point 5. And from there, if we get the isentropic compression, if we get to the isentropic compression, if we go for the isentropic compression, so what we are trying to do, what I told you in the previous lecture, that's always try to keep exit of the turbine above the entry to the combustion chamber. So that's why I am making a little bit changes here in that diagram, because it will help you realize the regeneration, because later we are going to see, we have seen the regeneration thing in the last lecture also, and today we are going to combine everything. So this is our 5 point. So our 6, we must place our 6 like that this is above the 4. This is above the 4 number point. Okay. So again, 5 to 6, what is happening? Isentropic expansion is happening. Okay. So this is the TS diagram 1, 2, 3, 4, 5, 6, 1. This is the TS diagram of our gas turbine cycle or Brayton cycle with intercooling. Got my point or not? So as I have told you in the previous lecture also, in the previous session also, that when we talk about the perfect intercooling, the temperature T3 must be equal to T1. So temperature T3 must be equal to T1. So I just have enlarged this figure so that all of you can comfortably see it. So in perfect intercooling, as discussed in the previous session, in perfect intercooling, we must have this condition satisfied, that T1 is equal to T3. It must happen. Okay, it must happen. Got my point or not? So when we say perfect intercooling, so perfect, with this word perfect, we have the idea that things are in a best possible conditions, means our network should be the maximum one, isn't it? When we talk about the perfect situation, so the perfect thing would be when we are getting the maximum output. So obviously in perfect intercooling, we are going to get the maximum network. So in order to get the network as maximum, so we require to have the compressor work should be minimum. Harshmala, you are asking T2 should be equal to T4 or greater than T4. So there's, in perfect intercooling, there is no such relation between T2 and T4 that we can universally say. You have to find it within the question on different cases. Okay, then we are going to see it only. What is going to happen. Okay, we are going to derive it. Okay, but as the input data, you can consider that T1 is equal to T3. But you cannot consider that T2 is also equal to T4. We are going to see what is T2, T4 happening. Okay. By this derivation, we are going to see. Don't worry. So whatever will come in front of all of us. Okay. No need of memorizing these kind of things. Just remember this, that T1 is equal to T3. Got my point? So now in order to have the network maximum, so we know this, that the network is turbine work minus compressor work, WT minus WC. Okay. So if WC is minimum, definitely W net is going to be maximum. Okay. So let us write the equation of compressor work. So it must be the compressor work of first stage compressor plus compressor work of second stage compressor. Obviously, we have two compressors now. So the total work to be consumed by the compressor units shall be added, WC1 plus WC2. Is it true or not? Got my point? So what is our WC1? WC1 is CP T2 minus T1, and WC2 is CP T4 minus T3. So we can write like this, T4 minus T3. So T4 plus T3. I just have taken CP common and writing the equation. Got my point or not? Got my point or not? Tell me. Got my point or not? And this is plus. This is plus. We are adding them. Na? This is not subtraction. So this is minus. All right. This is minus. All right. Because we are adding na WC1 plus WC2. So this is WC1, CP T2 minus T1. And this is WC2, T4 minus T3. Now, as I told you in the previous sessions also, whenever we see something like minimum and maximum, we have to create something like the maximum minima concept. So we need to develop this expression into some variable, and we need to differentiate it and put it equal to 0, as we do in the concept of maximum minima usually. So let us see what we can do. So firstly, T3 and T1 is equal. T3 and T1 is equal. So can we write it like this? T2 plus T4, T2 plus T4 minus 2 times T1. Can we write something like this? Is there any problem? Is there a problem? So there is no problem. So what we want that what would be the intermediate pressure? What would be the intermediate pressure if we have a lower pressure and a higher pressure? So what kind of a question can be asked from this, that if our lower pressure or our cooler pressure is this, and if our higher pressure, that is combustion chamber pressure, is this, what should be the intermediate pressure, so that we get the minimum compressor work, or we obtain maximum work output, maximum work net. So for it, you can either convert it in terms of what, in terms of pressure right here, right now, or you can go and solve for the temperatures first, then you can get your pressure. So choice is yours. So let us say in this, I told you T1 is constant only. So let us just convert into pressure, because in temperature we have seen where in the last session derivation of maximum work, we have seen in terms of temperature. So let's do this in terms of pressure this time. So we have T2 by T1 plus T4 by T1 minus 2, and you know T1 is constant only. Yes or no? Because we see the minimum temperature in a cycle, we keep it as constant. All right. So can we replace T2 by T1? Can we replace T2 by T1 with P2 by P1, or that we call as P2 by P1? or let me use this word Pi. Let me use this as Pi. So can we write like this? Pi by P1 to the power x. So just to simplify the expression, I have used x as gamma minus 1 by gamma. Okay, in isentropic we can use this relation. No, we have done it yesterday also. In the previous section also we have done it. Yes or no? In the previous section also we have done it. So we have this Pi by P1 to the power x, and here also T1 T3 are equal. T1 T3 are equal. Yes or no? T1 T3 are equal. So we can write T4 by T1. We can write T4 by T1 as what? T4 by T1 as what? So we can write it like P3, that is higher pressure. That is higher pressure. Okay, that is higher pressure by Pi, that by Pi to the power x again. Can we write like this? Can we write like this? Minus 2. Is there a problem? Because T1 is equal to T3. So let's just see here. So we can write like this, no? T2 by T1. I am applying this isentropic condition between 1 to 2. So it will be equal to P2. So in intermediate pressure, I am calling as Pi. Pi to the power 1 to the power gamma minus 1 by gamma. So we are calling it as x. All right. And between 4 and 3, so T4 by T3, we can write like this. We can write like this, that P4 by Pi, P4 by Pi to the power x, to the power x. Yes or no? So we can write here I have used P4, P3, so we have represented it by P4. So just to avoid the confusion between 1, 2, 4, 3 and all, can I write here the lowest pressure in the cycle? Can I write here the lowest pressure in the cycle? And can I write here the highest pressure in the cycle? Will that be fine? Will that be fine? Otherwise we may be confused in this 2, 3, in the game of 2, 3, 4 and all. Yes or no? So I am writing here pH by Pi, and I am writing here Pi by PL. Is that fine? Is that fine? So that we have no confusion. So Saurabh Patel, you are asking, sir, from where can we practice the question of steam turbines and steam nozzles? So my dear, you can go and see the Pekinag book of power plant. That can be one option. Okay. Secondly, you can go for seeing the ESC previous year objective questions. That can be the second option, but I would prefer the first option because, as you know, GATE is a numerical based paper. So in ESC objective, mostly questions were theoretical type of 1 mark. So that you can also do. Okay. And if you have seen all the sessions, you will be able to do it quite quickly because simple questions have asked. That what do you mean by 50%, which turbine is 50% reaction turbine? This kind of question are being asked over there. Okay. So from there you can certainly practice. Okay. To practice the questions of nozzles, you can refer Dr. Pekinag's book of power plant as well. You can refer R.K. Bansal book of fluid machinery as well. And you can refer Indian Space Research Organization, ISRO previous year papers as well, because there also you will be able to find the previous year questions of compressible flow. Okay. But I think for GATE preparation, if you go for Pekinag book or R.K. Bansal book, that would be great. For nozzle question, you can refer from both Pekinag book and R.K. Bansal sahab book. And in steam turbines, for steam turbines, you can go for this Pekinag sir book. All right. So now see, we have this expression. So in this T1 is constant, PL is constant, pH is constant. So only variable we can see here is our intermediate pressure. Only variable we can see here is our intermediate pressure. So you just differentiate it and put it equal to 0, you will have your condition in which you get your minimum compressor work and hence maximum net work and hence maximum net work. So can you please do it? Can you please do it? So I certainly know that you can do it. So I am writing the result directly. So you will be having Pi is equal to under root PLPH. Pi will be equal to under root PLPH. So what is the understanding we obtain from here? That if we require perfect intercooling or if we require the minimum work consumption in the compressor, minimum work compression in the minimum work in the compressor, minimum work in the compressor, what we can do if we want to have minimum work in the compressor or we want to maximize the network in intercooling cycle, we must compress or we must use the intermediate pressure by this relation under root PLPH, under root PLPH. So let us say now somebody of you was asking me about the temperature. So if perfect intercooling, now the students who are live can cross check. The students who are live can cross check this relation also. So first you cross check. This is the same as we have derived for maximum work done in ideal Brayton cycle. In ideal Brayton cycle, we have derived for the maximum work. In ideal Brayton cycle, we have derived in the condition of maximum work. There we have temperature. There we have temperature T2 as under root of minimum and maximum temperature. Here it is pressure, my dear. Here it is pressure, my dear. Here it is pressure, my dear. Got my point? Got my point or not? Okay. So now please cross check this. Cross check this if you are getting this or not. And meanwhile, do not forget to like and subscribe. Like and subscribe the GATE Academy. Do not forget to like and subscribe the GATE Academy. All right. All right. So live students can respond to me. Is this coming right or wrong? Is this coming right or wrong? Tell me, is this coming right or wrong? If you are derived it. So I think it is coming to be right. I think it is coming to be right. Okay, now tell me if we want to analyze the temperatures as well. If we want to analyze the temperatures as well, so T2 by T1 will be equal to P intermediate upon P lower. Is that true or not? P intermediate upon P lower to the power gamma minus 1 by gamma, to the power gamma minus 1 by gamma. Yes or no? Yes or no? So in case of perfect intercooling, what will happen? In case of perfect intercooling, when we have this perfect intercooling thing, we will be having this T4 by T3, or we firstly let's just see here. So T2 by T1. So if I put in case of perfect intercooling, can we say it is coming out to be root over, let us place the value of Pi. So it will be under root PLPH upon PL to the power gamma minus 1 by gamma, to the power gamma minus 1 by gamma. So T2 by T1 is equal to root over pH by PL, we can say. Root over pH by PL, we can say, by applying simple mathematics, to the power gamma minus 1 by gamma. Yes or no? Yes or no, to the power gamma minus 1 by gamma. So from here, you can also find the temperature, intermediate temperature, that is T2, to the temperature at which you want to compress your air. Yes or no? But I'm not recommending you to memorize all these. Do not memorize all this, because firstly, it is in the perfect intercooling case. So when there is a perfect intercooling case, just remember, when there is a perfect intercooling, just remember that our T1 is equal to T3, our T1 is equal to T3, and if T1 is equal to T3, everything can come. And also, if you want to avoid the derivation, just one more thing you can remember, that Pi is equal to root PLPH. Pi is equal to root PLPH. And if you don't want to memorize, you can also derive it quickly. You can also derive it quickly. So if we having the perfect intercooling, if we are having the perfect intercooling, T2 by T1 will come out to be like this. T2 by T1 will come out to be like this. So T4 by T3 is also what? T4 by T3 is also what? Or let me say T3 by T4 is what? Okay, let's just use this. So T3 by T4 is what? T3 by T4 is what? It will be equal to pH upon T3 is at intermediate pressure, Pi to the power gamma minus 1 by gamma. Isn't it? Isn't it? Isn't it? Okay. So here, for case of perfect intercooling, as we are talking about, for the case of perfect intercooling, can I place the value of Pi? Can I place the value of Pi as under root Pi pH, as under root Pi pH, and we have this value as gamma minus 1 by gamma. So from here you can say that T4 by T3, here you can say T4 by T3 is equal to under root, this is PL actually, under root pH by PL, under root pH by PL to the power gamma minus 1 by gamma, to the power gamma minus 1 by gamma, okay, to the power gamma minus 1 by gamma, okay, all right. So from this, you can see that these two relations are same only. Let's say this is equation number 1, and let's say this is equation number 2. So what other results are coming? So we can say from here that the ratio of T2 by T1 is equal to T4 by T3. Don't use all these results in general intercooling, but in perfect intercooling only, as we have discussed. So this is the case of perfect intercooling. So in case of perfect intercooling, can we say T2 by T1 is equal to T4 by T3? T2 by T1 is equal to T4 by T3 is equal to under root pH by PL to the power gamma minus 1 by gamma. Sometimes these relations can be asked directly. Okay, so you know how to derive it. So as we know, in case of perfect intercooling, T1 is equal to T3. So we can also say that T2 is also equal to T4. As Ash, you were saying, so I told you we do not have to memorize it, but we can come to it. Okay, so we have now T2 is equal to T4. So can I say the case of intercooling and perfect intercooling is clear? And have this factor of safety whenever they say intercooling, do not consider it perfect intercooling unless they say it. So we have this T2 is equal to T4. So is that everything clear till this point? Are we able to understand this intercooling cycle? Yes or no? Yes or no? Tell me. Those who are live can respond to me. And why we are seeing all this? Why we are seeing all this? Because we are making our way to the actual gas turbine cycle. So unless you understand the ideal cycle, yes, this is possible in case of perfect intercooling only. So unless we make ideal cycle clear, we cannot go for the actual cycle. So we are making some of the basics, or we can say we are making our path towards the actual gas turbine cycle. As already we have discussed this turbine thing in the steam turbine session. Okay. Yes, Harsh, you can differentiate work also, but in differentiating work, our turbine work is not getting changed na? In intercooling. Let's say, what are the effects of intercooling? So net work is turbine work minus compressor work. So turbine work to remain constant. There is no effect on the turbine work, no? There is no effect on the turbine work while we do intercooling. We have established this. So there is no effect on the turbine work, so it will remain constant. So if you differentiate, if you differentiate, if you differentiate the network formula, then you have to take turbine work as constant only. So it will come 0. So the answer will be same only. Got my point? So let us move to the reheat cycle. Reheat cycle. Got it, Harsha, or not? Or we can say reheating in gas turbine cycle. Reheating in gas turbine cycle. Reheating in gas turbine cycle. Okay. So this is the last case. Then we will be combining all the things: regeneration, reheater, intercooler. We will solve some questions. We will solve some question of ideal cycle. Then we will move to the actual gas turbine cycle. And once the actual gas turbine cycle is completed, within 5 minutes, 10 minutes discussion, we can conclude the whole series. Okay. Okay. So we are now moving towards the end of this series. We are moving now towards the end of this series. So please hold. Okay, we will have some questions solved so that it is whatever we are teaching is completely understood. So for that, we will solve some question as well. So this is our reheat cycle in gas turbine cycle. So why do we do reheat? So in the previous session also, I told you we do reheating and intercooling to increase the network output. Increase the network output. All right. So in intercooling, what was happening, that network output was getting increased because the compressor work was decreasing. But here by reheating, we increase the network, we increase the network by increasing the turbine work. So in reheat cycle, the turbine work is increased, is increased, and the compressor work remains constant. It do not change. It remain constant. All right. So why we use reheating cycle? It is air. Yes, it is mostly air, because this Brayton cycle we usually use in aircrafts. Okay, so it is mostly air. All right. So network done is increased in this case. Yes, network done is increased in the case of reheating because the turbine work increases. Because of this turbine work, this increase of turbine work. So let us make the cycle, or let us first make the arrangement of it. So here again we have a compressor. So instead of compressing it in 2 stages as we have done, in the intercooling, we are compressing it in 1 stage, So after this compression, it is going to the combustion chamber as usually. Then we are expanding it in 2 stages of turbine. So let's say we have turbine 1. So the entry to the turbine 1 is at 3. Now after expansion from this turbine, it goes to a reheater, which is again a constant pressure device, and as the name suggests, it is adding the heat into the system. So constant pressure heat addition is happening inside the reheater. So after our air leaves from the reheater, it enters to the next stage of turbine, and we call it turbine 2. We call it turbine 2. And after the expansion, after this expansion process from the turbine 2, it goes as usually we have seen. We are putting this cooler just to make the cycle. Otherwise, mostly it is open cycle. So this is our reheating cycle. This is what? This is our reheating cycle. Got my point or not? Got my point or not? So in intercooling, what we were doing, we were compressing our air into two stages. Here, what we are doing, we are expanding our, we are what? We are expanding our air in two stages. So let us quickly make the TS diagram. Let us quickly make the TS diagram. So I hope the students who are live can respond to me. Is this clear or not? The arrangement of reheat cycle is clear to you or not? And I hope if you have attended all the lectures, then yes, pressure is constant. As I said, in reheater is also a constant pressure device. Constant pressure device. Okay, so our game is again in three pressure lines. Our game is again in three pressure lines. So let us first make three pressure lines. Let us first make three pressure lines. Okay, so in this cycle, what is happening? Compression is happening in one stage only. So our air reaches from the inlet pressure to the maximum pressure in one stage only. So we are reaching this 2 point in one stage. In one stage. Okay. Then we have a combustion chamber. So in a combustion chamber, what is happening? Combustion chamber, what is happening? We are adding some heat. So it is reaching to this point 3. It is reaching to this point 3. Okay. Okay. Then what is happening? We have our expansion. We have our expansion taking place. We have our expansion taking place. So we have our expansion. So our air is expanded. Our air is expanded. Our air is expanded from 3 to 4 in first stage turbine. Then there is a reheater zone. So in reheater, what is happening? In reheater, what is happening? Constant pressure heat addition is taking place. So we are reaching to this point 5. At 5 again, a turbine will come into picture, and again expansion will take place. Again expansion will take place, and you will reach to this point 6. You will reach to this point 6. Okay, point 6. And as I told you already, I have told you, always try to keep the exit point of the turbine above the entry point to the combustion chamber. This will help you in the case of regeneration. We have already seen what is regeneration. So we have this 5 to 6. We have this 5 to 6. Okay. Then we have this 6 to 1. We reach from 6 to 1 in a cooler. We reach from 6 to 1 in a cooler. So this is our reheat cycle. This is our reheat cycle in which we are expanding in two stages. All right, yes or no? I have just enlarged it a bit. So all of you can have a good look. All right. So this is how we can make our TS diagram. Similarly, if we want to make our PV diagram, let us do it. So this is our PV diagram. From 1 to 2, compression is taking place, and we are doing the compression in one stage only. So highest pressure reaches just after the end of the compression process. Then 2 to 3, we are adding heat at constant pressure. Then 3 to 4, we are expanding in the first stage compressor. Then 4 to 5, again heat is added at constant pressure. So heat is added, volume will increase, pressure will remain constant. Then 5 to 6, again compression is happening, and 6 to 1 is the intercooling. So let's just see, as we have told you, that while reheating, our turbine work increases. With the reheating, our turbine work increases. So let's just compare it with our Brayton cycle in which no reheating is there. So directly we are expanding from 3 to this 4 dash point. Okay. Ideal cycle is this though 1, 2, 3, 4 dash 1. Ideal cycle is 1, 2, 3, 4 dash 1. Okay. So if we are expanding in only one turbine, or if we are using only one turbine, we are going to get this much work, as I am making it with the red line. So in the ideal cycle, are we getting this much work? Are we getting this much work or not? Because in open system we know work done in a process is the area under PV diagram when projected on the pressure axis. So when we project it on the pressure axis, we are getting this much work if we are expanding directly from 3 to 4 dash. Okay, so we are expanding in one stage as we do in the ideal Brayton cycle. But as you can see in the reheat cycle, our curve follows 3, 4, 5, 6, 4 dash. So if we are having the reheating cycle, can you say this is the extra turbine work we obtained? This is the extra turbine work we obtained in comparison to this green region is the extra turbine work we have obtained. Yes or no? This green region is the extra turbine work we have obtained. Yes or no? Tell me. So can we say from seeing this PV diagram that our turbine work is certainly increased with the use of reheater in the Brayton cycle, with the use of reheater in a Brayton cycle? Is that all right or not? Is that all right or not? Tell me. Is that all right or not? Tell me that. Is that all right or not? Okay. Okay. So from this discussion, we can certainly see that our turbine work increases. Now let us write the efficiency formula. Now see very, very carefully. Let us write the efficiency formula. So as I have told you, we can use this efficiency from the basics. We can write this efficiency from the very basics. So efficiency is what? Turbine. So we have two turbines. So let's say turbine work 1 plus turbine work 2 minus compressor. So this is our net work done. Upon heat added. In general, this is our efficiency, no? So with the reheater, I will use the subscript as RH. So with reheater, we have this much efficiency. Okay, so be careful here that WT1 is what? CP I am not taking into consideration because CP will be cancelled out. So we will be having T3 minus T4. Okay, or you can write H3 minus H4. Later you can do CP T3 minus T4 plus WT2. WT2 is what? The T5 minus T6. Compressor work is what? We have CP T2 minus T1. So like we can write like this T2 minus T1. Okay. Upon heat added. So you people or sometimes students can make mistake here that they will take only combustion chamber heat addition here, as we do in the ideal Brayton cycle, that you will say, sir, heat addition is happening between 2 and 3, so T3 minus T2. So let me tell you, in the reheater, I am highlighting this reason. In the reheater also, this is the heat addition or not? This is the heat addition or not? Tell me, this is the heat addition or not? The reason I have just highlighted by using a green highlighter. So this is also a heat addition, no? So this kind of silly mistakes sometimes happen. So I am writing it with the red pen so you can recognize that there is some danger here or there is a scope of mistake here. So do not forget this. Do not forget to write the heat addition in the reheater also. So we have the efficiency in the reheat cycle. Okay, got my point how we have written the efficiency. So you can use your basic principle. You can use your basics principle. No need of memorizing all those formulas, but you can have your basic principle. If your basic principle are strong, then you can do it with the basic principle only, and then from here you can go on finding all these temperatures: T1, T2, T3, T4, T5, T6. All the temperatures you can now find, and you can put it into this efficiency formula and get your efficiency. Is that correct or not? Are you able to get my point or not? The live students can respond. All right. All right. So now let's just see the effects of reheating, as we have seen. The effects of what? As we have seen the effects of intercooling. So if we see the effect of reheating, let us make here the ideal cycle. So this is our ideal cycle 1, 2, 3, 4-1. 1, 2, 3, 4-1 is the ideal one, and 1, 2, 3, 4, 5, 6, 1. 1, 2, 3, 4, 5, 6, 1 is our reheater one. So our cycle 1, 2, 3, 4-1 is the cycle without reheater, and our 1, 2, 3, 4, 5, 6, 1 is the cycle with reheater. So if we compare here in the original cycle, let us first see the heat rejection here. So in the previous section, I have showed you how to compare the efficiency by using the fundamentals of mean temperature of heat rejection and mean temperature of heat addition. So let's just see here. So between 4-1, between 4-1, can we say that this is our TMR1? Because as I told you in the previous session also, that we can see our mean temperature somewhere in between the 2 points. Mean is like that only, no? Mean is the average. So if you are doing average of 2 points, you have to be somewhere in between those 2 points. So between 4-1, we are somewhere here. So this is the mean temperature of heat rejection of the cycle without reheater, Now if we see that we are having this reheater, so our cycle is from 6-1. So can we write like this? So between 6-1, this is our somewhere in middle. This is our mean temperature of heat rejection. As I have highlighted it. Yes or no? So what is the effect of reheating? So you can say by reheating, mean temperature of heat rejection reduces. Can we say like this? Mean temperature of heat rejection reduces. Yes or no? Okay. Now what about mean temperature of heat addition? So in the original cycle means the cycle without reheater. We have our mean temperature of heat addition somewhere here. Yes or no? This is the mean temperature of heat addition somewhere here between 2 to 3. Now some people will be confused, sir, in the reheater cycle, it should also be there only. No. So don't forget this green highlighted part of the reheater, that we are adding the heat from 2 to 3 as well as 4 to 5. So we are adding heat here in 2 places. So combined average definitely between 2 and 3 and 4 and 5, the combined average definitely is going to be increasing. So this is our TMA2. This is going to be our TMA2. So what is the effect? Here we are having? What is the effect on mean temperature of heat addition? So TMR decreases, but TMA increases. Okay, so what we have established in the previous session, if mean temperature of heat rejection is decreasing, the efficiency should decrease. And if the mean temperature of heat addition increases, the efficiency should increase. So here what we can say, as we have seen in the intercooling cycle, in intercooling cycle, the mean temperature of heat addition was increasing. Okay, okay, let's just go there. So in the intercooling cycle, what we were seeing, that mean temperature of heat addition was decreasing and mean temperature of heat rejection was also decreasing. But the rate of decrease of mean temperature of heat addition is more. That is why the overall effect, that is why the overall effect, that is why the overall effect on the efficiency is decreasing. Okay, so here also TMR is decreasing and TMA is increasing, but the decrease of TMR is more than the increase of TMA. So hence we can say overall the efficiency by applying reheater in a Brayton cycle reduces. Okay, so the overall efficiency of the plant reduces when we apply the reheater. Got my point or not? Got my point or not? Yes or no? Yes or no? Yes or no? Tell me. Yes or no? Tell me. Is that clear till this point about mean temperature of heat rejection, mean temperature of heat addition? I am seeing your responses. Okay, so I consider it to be clear. I consider it to be clear. Okay. Now, if somebody will say, if somebody will may say that, sir, we have seen the perfect intercooling, so there must be some perfect reheating kind of thing as well. There must be some perfect reheating kind of thing as well. So what do we mean by perfect reheating? What do we mean by perfect reheating? So in perfect reheating, what happens that T3 will become equal to T5. T3 will become equal to T5 and the turbine work will go to maximum. The turbine work will go to maximum. So again we can do what we have done in the intercooling cycle. We can derive the expression. We can write turbine work. So turbine work is what? Turbine work is what? Cp T3 minus T4, T3 minus T4 plus work is happening in two stages, no? Cp T5 minus T6. Okay. Okay, so we have to maximize it. So again, you can follow the same procedure. Again, you can follow our same procedure. Again, you can follow the same procedure. Again, you can follow the same procedure and differentiate it with respect to some variable. So you can convert it into the pressure ratio, then can do it as well as we have seen in the intercooling cycle. But I believe you guys that you will be able to do it. So what result you are going? I'm directly writing the result. So the result is very much similar to what we get in the intercooling cycle. That is why I have derived and showed you the way how to do it with intermediate cycle, with intercooler cycle. Okay. So here again for perfect reheating, what should be the condition? That your intermediate pressure must be root over PL by PH, as we have seen in intercooling cycle. As we have seen in intercooling cycle. Got my point or not? Got my point or not? So once you can have your intermediate pressure, you can solve for all the temperatures. You can solve for all the temperatures, put the values of temperature in whatever you want to find out. Either it is turbine work, compressor work, efficiency, whatever. Okay, so you can once you have your intermediate pressure value, you can solve for all the temperatures and you can put all the temperatures value at different formulas, and no formula you need to remember. No formula at all you need to remember. Got my point or not? Just take care of it, this intermediate pressure thing, and as it is same in both intercooler and reheating, you can simply have this kind of idea in your mind so that you can directly use it also when times come. So is the reheating cycle cleared or not? Is the reheating cycle cleared or not? Cleared or not? So we have seen regeneration alone. We have seen regeneration alone. So if we summarize all these things in regeneration alone, what was happening? What was happening? In regeneration alone, our efficiency increases. In intercooling alone, if we see the intercooler is used alone, we may see that our efficiency decreases. And in reheating alone, we can say in reheating alone, our efficiency decreases. So we combine all these three. So when we combine all these three, remember the efficiency increases. So now let us make the combined gas turbine cycle with regeneration, reheater, and intercooler. So let's just try to understand. The arrangement. So as intercooler is there, we will be having two compressors. So let's say C1. So our air is entering into C1 and going into the intercooler. Okay. From this intercooler is going to get into the next stage compressor. From this next stage compressor, it is going to the combustion chamber. As we see it. Okay, so this is point 1. Let's say this is 2. Let's say this is 3. Let's say this is 4. So we are going to the combustion chamber. From the combustion chamber, we are exiting at the point 5. From the combustion chamber, you are going to your first stage turbine, that is T1. Then you are going for a reheater. So you are going, this is 6. So this is reheater, this is 7. After this reheater, you are having your second stage turbine, that is T2. Now from this T2, we should bypass it. We should send it to the regenerator, as we have seen. We send the exhaust steam. Okay, so here comes the regenerator. We have seen all this in the previous session, how the regenerator works. So we have a regenerator here. So the fluid or the high temperature exhaust gas exiting from the turbine goes to the regenerator, and provide is heat energy to the entering air before the combustion chamber. So this way we can increase the efficiency. So this is what? This is regenerator. So let's say from 4 to A, we have this regenerator, and here from A to B, we have this regenerator. So in the previous session, we have seen everything, effectiveness, everything and all. And here we have this combined cycle in which we have combined intercooler, reheater, as well as the regenerator. So I want you to make that diagram of TS diagram. Do not make PV diagram. If you want to make PV diagram, it is okay. You can make the PV diagram also. But I am giving you, to those who are live, I am giving you some time to draw the TS diagram of it, because drawing the TS diagram correctly is also very, very important part. Now just do it. Start doing it. You can start doing it. So I am taking a pause here of 2 minutes. If you are liking this series, please like and subscribe the GATE Academy channel. Please also like and subscribe the GATE Academy channel. So those who are live are making this, I think, that TS diagram of this combined cycle. with intercooler, reheater, and regenerator combined. So let's quickly make it and write the expressions for efficiency. Then we can have some questions solved on the ideal gas turbine cycle, and we can now then move to the actual gas turbine cycle, and then we can finish this series. Then we can finish this series completely. Then very nice. So let me make the TS diagram. Let me make the TS diagram and write the efficiency. Let me make the TS diagram and write the efficiency. So again, we have three pressure lines. Again, we have three pressure lines because our game is between three pressures. Game is between three pressures. Now try to understand this. Now try to understand this. So we have these three pressure lines. So from 1 to 2, what is happening? There is a compressor. There is a compressor. There is a compressor, so our compression is taking place. There is a compressor, so our compression is taking place. Our compression is taking place, and here also we have to have some more inclination because we want to put this 8 point above. We want to put this 8 point above this. Above what? Above the entry temperature to the combustion chamber. Then only there will be a scope of. So let me make it a little more inclined. So these, let's say, are our three pressure lines. I have given them some more inclination, and these are not straight lines actually, they are curves kind of. So this is 1 to 2 in our compression. What is happening? Pressure increases, temperature increases, entropy remains constant. So when it goes to the intercooler, constant pressure heat rejection takes place. So entropy reduces, temperature reduces. From 3 to 4, what is happening? We are again compressing it. Now from 4 to 5, what is happening? From 4 to 5, what is happening? We have our combustion chamber. Then 5 to 6, what is happening? We have our first stage turbine. Then 6 to 7, what is happening? We have our reheater. In which we provide heat, or we add heat addition. We do heat addition in the air. So when heat addition is taking place, our entropy increases, temperature increases, we reach to this point 7. Now from 7 to 8, what is happening? We have our exhaust turbine. We have our exhausted turbine from the second stage. So as you can see, just please make sure your T8 is greater than T4. Always make sure that your T8 is greater than T4. Okay. So when the air exited from the turbine, it has high temperature. So as I explained in the previous session also, that regeneration scope will be there only when the exhaust temperature gas is higher than the temperature of air entering to the combustion chamber. Okay. So our air exiting from the turbine, the second stage turbine, will give its heat energy to the fluid entering to the combustion chamber, to the air entering to the combustion chamber. So when heat is given to the air at 4 point, its temperature will increase, and if there is perfect regeneration, this A will become equal to 8. Otherwise effectiveness will be given to you. Similarly, when the stream exhausting from the gas turbine given the heat to given the heat to given the heat to this cold fluid, its temperature will reduce and your temperature will reduce to B. And as we have seen in the previous session in regeneration, it is not no, generally yes today. In the actual cycle, there will be pressure losses, but the ideal cycle, in the ideal cycle, we require to maintain them at same pressure. We require to maintain them at same pressure. Okay, okay. So now this is the B point. This is the B point. This is the B point. Okay. So the complete cycle you have in your screen is 1, 2, 3, 4, A, 5, 6, 7, 8B1. This is your complete cycle with all the spices in it. Intercooling is there, regeneration is there, reheating is there. So everything is here. Now quickly let's just write the efficiency of it. Let's just write the efficiency of it. So it is going to be T7 turbine work. So turbine work is between T5 to T6. So it will be T5 minus T6 plus T7 minus T8 plus T7 minus T8. Okay. Minus compressor work. So let's say we have two compressors. So two works we are having. I already have taken CP common, so it will be cancelled out. So this is compressor work of 1 minus T4 minus T3. This is compressor work of 2. No memorizing required, just the basic concept. Upon input. So what is our input? Heat is added in the combustion chamber from 8 to 5. So this is the heat added in the combustion chamber, T5 minus TA, plus the heat added in the reheater, that is T7 minus T6. So this will be the efficiency of this combined cycle. So as you can see, there are so many temperatures there. So you cannot memorize this as far as I feel. So it is better to do it with your basic concepts. Is that clear or not? So from this, I can say that regeneration, intercooling, reheating, everything is clear to you. True or not? True or not? So this is what ideal cycle is completed. This is ideal cycle, complete ideal cycle with all the possible cases. So what cases we have seen? Firstly, what we have seen in the gas turbine cycle analysis. Firstly, we have seen that how ideal Brayton cycle works. Then we see the effect of pressure ratio on the efficiency as well as the work done. Then we have derived the expression for what? We have derived the expression for maximum work that can be obtained and what shall be the pressure ratio, optimum pressure ratio for that. Okay. Then we see the regeneration, the effects of it. Then we have seen the intercooling, the effects of it. Then we have seen reheating alone and the effects of it. And now in this, we have simply combined everything and together, and we have created a cycle in which everything is happening ideally. Everything is happening in ideal conditions. So let us take some questions now from the ideal cycle. So we have better idea about it. We will get the better idea about it. So let's do this first question. Those who are live can do it with me right here, right now. We will be having some questions of this ideal cycle so that gas turbine cycle is clear to us. Okay. So first, see the approach is my approach in this gas turbine section, because we have completed the turbine part already. In the study of steam turbine. You already knew compressible flow there. You already knew making the velocity triangle there. You already know impulse reaction turbine there. You already know the expressions of efficiency there. So everything you know already. So we are analyzing the cycle, and we try to reach to the actual gas turbine cycle. Okay, so for that, For that, it is required that we first understand the ideal cycle well. Then only we will move to the actual gas turbine cycle. Okay, so just do this question, very simple question. I hope you all can do it. I hope you all of you can do it. Simple question, simple ideal Brayton cycle question. It is a simple ideal Brayton cycle question. Can we have it? Can we do it or not? Tell me. In this, we have to find the mass flow rate. Those who are live in this session can respond to me, and those who are seeing this video can also solve this question. So this topic will be clear to you. I am taking a pause here so that the live students can solve this question. And in this time, I will request you to also like and subscribe the GATE Academy channel if you are liking this whole series. Live students can give me the answers. Live students can give me the answer to this question, please. So see, whenever you do question of cycles, it is always necessary or it is always recommended to make the cycle first. It is always recommended to make the cycle first so that everything will be in front of you, so that everything will come in front of you and you make no mistakes. So let us draw the TS diagram of it. Let us draw the TS diagram of it. So we have this TS diagram of the Brayton cycle. We have this TS diagram of the Brayton cycle. So what is given to us? The pressure ratio is directly given to us. RP is equal to 4 is directly given to us. And we require the airflow rate for 300 kilowatt power output. Okay, so what will be the power output? So we know the net work output or net power output is turbine minus compressor in case of Brayton cycle. We have seen it in the previous session also. So turbine work is Cp T3 minus T4. So our net work in kilojoule per kg we are going to get as Cp T3 minus T4 minus Cp T2 minus T1. So this is our net work done in the units of kilojoule per kg. This is net work done in the units of kilojoule per kg. Got my point or not? This is the net work done in kilojoule per kg. Now, if we say, sir, power. So power will be m dot into network, m dot into network. Say yes or no? M dot into network. Yes or no? So our power is going to be 300 kilowatt. 300 kilowatt. So it is, let's put it in the kilowatt only, and m dot. So what do we require? We require all this W net. So for that, we require T3, T4, T2, T1. So if you see in the question, we are given with the T1 value. So T1 is 273 plus 27. Very nice. Yes, your answer is correct. Vijay, your answer is also correct. So our T1 will be 300 Kelvin and our T3 is given to us as 1000 plus 273, that is 1273 Kelvin. Okay, so if we can find T2 and T4, we will have our answer. So we know T2 by T1 is pressure ratio, that is P2 by P1 to the power gamma minus 1 by gamma. So from here we can have our value of T2 if we have T1. So that value of T2 is coming out to be 857 Kelvin. Value of T2 is coming out to be so value of T2 is coming out to be, let's see, is coming out to be 857 Kelvin. Okay. Live students can correct me if I'm making a mistake of calculations. So T2 is 857 Kelvin. All right. T2 is our 857 Kelvin. Similarly, by T3 by T4, by doing this T3 by T4, by doing this T3 by T4, we can say that the pressure ratio is again gamma minus 1 by gamma, or you can simply equate T2 by T1 with T3 by T4, you will have your answer. So we have T3, so from here can we find, so there is a mistake, this T2 is not this, T2 is, sorry, my mistake, I have taken the wrong value. So it is 445.8 Kelvin. It is 445.8 Kelvin. So T4 we are going to get as 857 Kelvin. So that is same only 857.66 or 857 Kelvin. So from this we have the value of T3. So now we have the value of T2, T4, T1, T3. So can we put it here? Cp is given to be 1. So just put all the values here. So 1000 minus T4 is what? 857. T4 is what? 857 minus Cp we have taken common, that is 1. So minus T2 is 445.8 plus T1 is given to be 300. So now you can have your m dot value and it will come out to be 1.103 kg per second something. Kg per second something. Okay. Or we can say 1.108. So it is 1.11 kg per second. So got this question or not? This is a simple ideal Brayton cycle question. Why we are doing this question? Because as we have studied this much, so in order to T3 should be in Kelvin, sir. Right. T3 should be in Kelvin. I have put it into 1000. I have put. Okay. So let's just change it. It is 1273. It is going to be 1273. So from this you can have your mass flow rate. Now, can you attempt this question as well? We have seen this also. Work ratio, back work ratio. We have seen all these things. So now you can start solving this question, please. Those who are live can solve this right now. And those who are seeing the recording can also do it when you reach this point in the video. It will be beneficial for you. So let's do it. Those who are live can tell me the answer. I hope you guys remember. I hope you guys remember what is the back work ratio. I hope you guys remember what is the back work ratio here. So what is given in the question? Air enters a compressor of gas turbine operating on Brayton cycle at 1 bar 27 degrees Celsius with a pressure ratio of 6. Now calculate the maximum temperature in the cycle when back work ratio is 0.5. So what we have seen in the previous sessions, that back work ratio for a cycle, what we have seen in the previous sessions, that's a back work ratio. What is this? This is the back work ratio is the negative work in a cycle upon positive work in the cycle. So this is given to be 0.5. So let us, as I said, let us just draw while solving a question of thermodynamics of some cycle. You always should draw your TS diagram or PV diagram, whatever is required, so that you will make no mistakes. You won't make mistakes. Okay. Okay. So this is our Brayton cycle, ideal Brayton cycle. So back work ratio is 0.5. So we have compressor work. So our compressor work, CP we can cancel out. So compressor work is T2 minus T1 upon turbine work is T3 minus T4. Turbine work is T3 minus T4. Is that correct or not? Is that right or not? Okay. Okay, so this is given. Now what we have to calculate? We have to calculate this T3. We have to calculate this T3. We have to calculate. So this T3, if we use this equation, what else we require? We require to find T3. We require T1. We require T1. Okay. We require T2 and we require T4. If we have these three, we can have the value of T3 as well. Okay. So T1 is given to us. So let's just find T2. T1 is given to us. So T2 by T1 we know. Pressure ratio is given. So T2 by T1 is we know P2 by P1 or pressure ratio to the power gamma minus 1 by gamma. So gamma is given. Air it is saying, so we can consider 1.4. So gamma minus 1 by gamma, that is this much. So we can have the value of T2, yes or no? We can have the value of T2. So T2 is coming out to be 500.55 Kelvin. 500.55 Kelvin. All right. T2 is coming out to be 500.55 Kelvin. Okay. Now we have the value of T2 also. Okay. Okay. So now if we have to find the T4, we don't have T3 also, but we can use the relation of this pressure ratio. So we know what T3 by T4 is equal to pressure ratio to the power 1.4 minus 1 upon 1.4 minus 1 upon 1.4. So we have this one relation. So there are two variables left, T3 and T4. We have this equation where two variables left, T3 and T4. So you can put the value of T4 in terms of value. Your answer is correct, Yash. So if you put the value of T4 in terms of T3 in equation number 1, you will certainly going to get T3. So since we have the value of T1, T2, and this equation remains between T3, T4, and there is another equation which remains between T3 and T4. So being an engineer, we absolutely have this idea, we must have this idea that whenever there are two variables and we have two equations, we can solve them. So if you solve these two equations, and I am very much certain that all of you can solve, so you will get your T3 is equal to 1001 somewhat Kelvin. Okay. Okay, so your maximum temperature in the cycle will be 1001 Kelvin. Is that clear or not? Is that clear or not? Tell me. Is that clear or not? Is that clear or not? So now let's do this question. Let's do this question. Now we have one more question on the screen. Those who are live can respond to me. Those who are live can respond to me. Can solve this question, please. Those who are live can solve this question, please. And meanwhile, while the question is on screen, if you have not subscribed the GATE Academy channel yet, I request you to do it. You can tell me the answer. You guys can tell me the answer if you have solved it. If you have guys have solved it. So I am trying to cover all the cases I have taught you here. So the first question was of a simple Brayton turbine. Second question, we have seen something like work ratio, back work ratio. So simple second question was based upon that. We have seen the condition of maximum work done. So the third question is on the basis of that. All right. Now you can please solve it. You can please try and solve it. You can please try and solve it. In the previous session, we have seen the condition of maximum work. So this question is based upon that only. So what this question is telling us, sir, mass flow rate of compressor inlet is 2.5 kg. So mass flow rate is given to us, m dot is given to us as 2.5 kg per second. Given to us as 2.5 kg per second. Yes, you are right, Yash. Very nice. So this is given to be 2.5 kg per second. Inlet condition, that is P1. P1 is given as 1 bar. P1 is given as 1 bar. T1 is given as 27 degrees Celsius. The temperature at the inlet of the turbine is 927 degrees. So T3 is given to be 927 degrees Celsius. Then determine the maximum power and efficiency at that point. So if you remember, so let's just, as I told you, let's just make the Brayton cycle, because whenever you're doing a question of a cycle, power plant, refrigeration, IC engine, whenever you are making a cycle of in any of these subject, always try to make the figure. Always try to make the figure before you proceed, so that things will be in front of you and you will be able to apply your formulas nicely. Okay, so we have this 1 2 3 4 1. We have this 1 2 3 4 1. We have this 1 2 3 4 1 as our Brayton cycle. So in the condition of maximum work, in the condition of maximum work, yes, yes, your answer is correct. So condition of maximum work we have seen in the last session. Yes, Aishwarya, your answer is also correct. So what is the condition of maximum work we are having? What is the condition of maximum work? What is the condition of maximum work? So in the condition of maximum work, our T2 is equal to T4 is equal to under root T max T min under root T1 T3. We have seen this formula. We have derived this formula in the last session. Yes or no? T1 T3. All right. So if we have the value of T1 T3, so do we have? So yes, we have. Always remember to put them in Kelvin. Always remember to put them in Kelvin. So T2 you will be getting after you put them in Kelvin. So T2 you will be getting as 600 Kelvin, and that will be T4 also. These results we have developed there, no? Am I right? If I am making any mistake, live student can correct me. So this is T2 is equal to T4 is equal to 600 Kelvin. Now we wanted to have, we wanted to have, we wanted to have the maximum power. So the maximum power, for that, let us first calculate the net work done in kilojoule per kg units, in kilojoule per kg units, in kilojoule per kg units. So we have net work is equal to turbine minus compressor, turbine minus compressor. So we will be having Cp T2 minus T1. Sorry, we must subtract turbine work. We must subtract the compressor work from turbine work. So we must write like this. This is the turbine work minus the compressor work is T2 minus T1. That is T2 plus T1. T2 plus T1. Okay, just subtracted it. Just subtracted it. So it will be like this. Now you have the value of all the temperatures. Cp is given in the question as 1 kilojoule per kg Kelvin. So you have the value of all these temperatures Cp you are having. So you can form this network. So this network is coming out to be, as the value of Cp you have taken in kilojoule per kg. So this is going to come in this, like this, 300 kilojoule per kg. 300 kilojoule per kg. So power you are going to get is m dot into network, m dot into network. So your m dot is 2.5 kg per second, and if you multiply it with network done kilojoule per kg value, you will be getting 750 kilowatt. You will be getting 750 kilowatts. So this is the power you have obtained. This is the power you have obtained. And efficiency, for efficiency, you do not to remember any formula. You just go to your basics. You have the value of all the temperatures. So let's do like this on the basis of temperatures. So this is the turbine work. Cp we can cancel out because numerator denominator there will be Cp. So this is turbine work minus compressor work is T2 minus T1 upon heat addition. So heat addition is taking place between 2 and 3. So it will be like T3 minus T2. It is going to be like T3 minus T2. So you have the temperatures of at all the points 1, 2, 3, 4, everywhere you have the temperature. So you can find your efficiency, and if you put all these temperature value, your efficiency will come out to be 50%. So this is the third case we have seen in the previous session. In the case where we have discussed about the net, we have discussed about the maximum power. All right. So after then, we have seen the cases of regeneration, reheating, and intercooling. Reheating we have seen today only. So now let's just do one big question in which we have combined all these three cases together. So with this question, we can say that our ideal gas turbine cycle or ideal Brayton cycle is completed in all respect. Okay. So you have this question on your screen. Please read it carefully, draw the TS diagram, try to find all the temperatures and give me the value of efficiency and total turbine work output per kg of air. So now you can please solve it. Now you can please solve this question also. Those who are live can do it with me. Those who are seeing the video of it, who are not live, I also recommend them to solve it. Keep your copy and pen handy with you and solve it at this point, so that when I will solve it, and if you have made any mistake, you will be able to recognize it. You will be able to understand your mistake nicely. Okay. So understanding the mistake is very, very important. So this session, after this question, we will end this session and we will continue with the actual gas turbine cycle in our last session. So after 1 hour from 1 p.m., we are going live again for the last session of ours in this series of steam turbine and gas turbine, which is newly added syllabus. Although this part of gas turbine was already there in the GATE syllabus, but I have covered it here so as I can make you understand about the actual gas turbine cycle, about the gas turbines, impulse turbine, reaction turbine, nozzles. We have seen in the steam turbine part, you can directly use those information in case of gas turbines also. In gas turbine, the requirement is quite simple, that we want lightweight because we are going to use it in aircraft applications mostly. Okay. So one basic difference is there, that in gas turbine, stages are generally more than the steam turbine. Rest, velocity triangle, everything is same. Okay. It is also an axial flow device as our steam turbine is. So gas turbine is also axial flow device like our axial flow compressors. So axial flow compressors, velocity triangle, steam turbine velocity triangles and analysis, and gas turbine velocity triangle and analysis is kind of similar to each other. It's very much similar to each other. That's why in most of the books, you won't find the analysis of gas turbine if steam turbine is given, and you won't find the analysis of steam turbine separately if gas turbine is given. Okay. If you see the book by the Dr. P.K. Power Plant, you will find 1 or 2 para written over about gas turbine, that it is very much similar to like a steam turbine and all this. It is like velocity triangle confines to the axial compressor gas turbine, that is axial flow steam turbine only. If you see the gas turbines by Dr. V. Ganeshan, you will find whole thing written about the gas turbine. You won't find anything about the steam turbine. So there they have explained the same things what I have explained to you in these sessions. What I tried to explain you in this session in the GATE perspective, V. Ganeshan is a very, very good book for gas turbines or the analysis of impulse turbine, gas turbine, compressible flow and all. Okay, but you need not to refer it. If you want to refer it, you can go and buy it. Okay, okay. Otherwise, you can follow the sessions. And for GATE perspectives, as per my experience of 8 years, this much would be sufficient. But nobody can claim 100% that whatever I have taught, only this much can come. If somebody is saying like this, he's just fooling the students. Okay. So according to me, this much, whatever I felt right, I have taught you in this series. Okay. If you learn something more than what I have taught, it is very, very good. But at least learn this much what I have taught to you to cover, to get good rank in GATE examination. All right. So let me solve this question for you. So those who are live can take the screenshot of this question so that I can move the screen. So what is given in the question, in the regenerative reheat cycle, air enters the first stage compressor at 1 bar 300 Kelvin and it is cooled up to 290 Kelvin and 4 bar pressure in an intercooler. Okay. This line is unnecessary, I think. This we do not require. So in the regenerative reheat cycle, air enters the first stage compressor. So this is the conditions what we have. So let us write the given data right here. So P1 is going to be 1 bar. T1 is going to be 300 Kelvin. So we have P1, T1 given to us. Okay. It is cooled up to 290 Kelvin, that is T3. So let us make the cycle, then we will write the data. So we will be able to understand the data more nicely. So we have, let's see, so we have reheating, we have regeneration, we have intercooler. So we must make a combined cycle. We must make a combined cycle diagram. So once you have the diagram with you, you will be able to feel the things more accurately. So let me just copy it from there. Here because as we have already made it, no. So why to make it again? There are some benefits on teaching on the computer screen. Okay, now this is our diagram. This is our TS diagram. So now let's just locate the data, what we have, what we require. So let's just do it fastly. So we have this P1 given to us as 1 bar, T1 given to us as 300 Kelvin. Our intermediate pressure, that is P2. What is intermediate pressure? So P2, P3 is intermediate pressure. P6, P7 is also intermediate pressure. So all these pressures are given to us at 4 bar. Okay. Okay, so this P1 is also equal to P8. All right. This is also equal to P8. Do not get confused in all these things. Okay. And also what is given? Our P3, P4, P5 is also given. P4, P5 is also given as 8 bar. What else is given to us? What temperature? So we have T1 with us. We have T3 with us. In the regenerative reheat cycle, air enters the first stage compressor at 1 bar 300 Kelvin and it is cooled up to 290 Kelvin and 4 bar pressure in the intercooler. So we have T3 here with us. So T3 we have is 290 Kelvin. So this is not perfect intercooling. This is not perfect intercooling, because if it would be a perfect intercooling, then the temperature of T1, T3 must be same. Okay. It is further compressed to 8 bar pressure in second stage compressor. So we have taken this data. Compressed air is passed through a regenerator with effectiveness of 0.8. So the effectiveness of regenerator is given to us at 0.8. What else is given to us? So after combustion chamber, gas enter first state turbine at 1300 Kelvin. So we have T5 with us. T5 is 1300 Kelvin. It is reheated at constant pressure up to 1300 Kelvin. So we have T7 in this. That is equal to T7 in this. We have 1300 Kelvin. Okay, also this is given. And we have to find the overall efficiency. So before randomly solving the question, let's just write the efficiency so that we come to know what temperature is given to us and what we require. So we have efficiency as T7 minus T8, turbine minus compressor. Yes, practically, since it is given in the question, we can consider it. Practically, it is not most oftenly we do. Okay. Okay. But yes, it is possible. There is nothing like it is not possible, but this is not generally what we do. Okay. So now we have this turbine work plus turbine work combined T7 minus T8 plus T5 minus T6 minus compressor work, that is T2 minus T1 minus T4 minus T3. This is the compressor work upon the heat added, So heat added is T5 minus TA, because there is regeneration also. So T5 minus TA plus T7 minus T6 plus T7 minus T6. So now let's just see which temperatures we are given in the question and what we have to find. So T7 is given to us. All right, T5 is given to us. T3 is also given to us. T1 is given to us. Again, here T5 is given to us. T7 is given to us. So we require what temperatures? We require T2, we require T4, we require T6, and we require T8, and we require TA. So I am putting red mark. I am putting red mark on those, red tick on those which temperatures we require to find to solve this question. So let's just one by one start solving for them. So for that, do we require T2? Yes, we require T2. So let's just find T2. So we have T2 by T1. We have T2 by T1. We have T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. P2 by P1 to the power gamma minus 1 by gamma. Now we have all the pressure values with us. We have T1 with us. So can we find this T2 value? Can we find this T2 value? So this T2, you place the value of T1, P2 and P1. This T2 is going to come out to be 445.7 Kelvin. Those who are live can cross check it also. So this is going to be 445.7 Kelvin. So we have the value of T2 now. So we have this T2 now. So let's just put a red mark to green mark. So now we have the value of T2. Okay, we have the value of T2. Now we require the value of T4 also. We require the value of T4. So we know T4 by T3. T4 by T3 is equal to P4 by P2 to the power gamma minus 1 by gamma. to the power gamma minus 1 by gamma. Is that okay or not? Is that okay or not? So we have the value of T3, P4 and P2. Can we find the value of T4? So you will say yes sir, certainly we can. So we can find the value of T4. We can find the value of T4 and it is coming out to be 353.51. 353.51. Those who are live can tell me if I am doing it rightly or wrongly, or you can cross check the values as well. So we have the value of T4. So let's just erase our mark from T4 and put it a green line. Put it a green line over it. So we have now T4. Now what we require? We require T6. We require T8. So T6, T5 by T6 we know. T5 by T6 is P5 by P6. So if you go step by step, I think you will be able to understand it and solve it easily. You will be able to understand it and solve it easily. So we have this P5 by P6 to the power gamma minus 1 by gamma. So we have all the pressure values. We have the value of T5 given to us as we have seen it. So T5 is given to us 1300 Kelvin. So we can find the value of T6 from this. So T6 will come out to be 1066.4 Kelvin, 1066.4 Kelvin. So let's just highlight it also. All the temperature values we are highlighting. And let's just put a red mark to green mark on T6. So now we have this also. We have this also. So now only T8 and TA is required to be found. So T8, how we can find? Where is T8? So 7 to 8. So T7 by T8. We can write like P7 by P8 to the power gamma minus 1 by gamma. Okay. Now, since we are having the value of T7 and all the pressures, we can certainly find the value of T8 from here. So T8, if you find, it will come out to be 874.8 Kelvin. You can calculate with me. If there is any mistake, you can let me know. The live student can tell me. Yes, your answer is right. Yes, very good. So I am highlighting it, and let's just go there in the efficiency formula. So now we had this T8 also found. So I am putting a green light on it, green mark on it. Now we have only one thing left, that is TA. So TA will come with the regenerator effectiveness. So we have the effectiveness also. So let's just do that. So effectiveness is equal to TA. So where to apply the effectiveness? Effectiveness between 4 to A and 8 to B. 4 to A and 8 to B. So how can we write TA minus T4? We have explained this in the previous session also about the regeneration. So minus T8 minus T4, this is how we apply the effectiveness. Okay. Between the air entering to the combustion chamber and the air exiting from the turbine. So we have TA minus T4 upon T8 minus T4. Now we have the value of T4, we have the value of T8, we have the value of effectiveness. Can we find our TA from here? So yes, sir, we can find the TA. So if you find the TA will come out to be 770.57. So now you have the value of TA also. So let me put a green mark there also. So this is also found. So now all the temperature values are found. So if you place all the temperatures here, you will find your efficiency at 58.9%. So this is how very quickly we can solve it. When people see this big question, people say that this question is not very much probable in GATE examination. I will say this, bigger than this question can be asked. This is not that big to solve. So efficiency will be 58.9%. And now you are asked about the work done in the turbine. Okay, so work done turbine, when we call it turbine as a unit. So do tell the net work done. Do not trap that only turbine work you are asked. So net work done is Cp T7 minus T8 plus T5 minus T6. So in this question, what is written? Total turbine work output is written. Total, so you have to calculate, you have to calculate the turbine work, because directly it is turbine only written there, na? Network or turbine unit, the complete unit, if it is written, then you have to find the network then. So here let's find the turbine work output. So it is T7 minus T8 plus T5 minus T6 Cp. So if you put all the temperature value, you will get your turbine work as 662. You will get your turbine work as 662 kilojoule per kg. And if you have the temperatures value, you can also get the compressor work, net work, whatever you want. Compressor work, net work, whatever you want. So is that clear or not? The live students can respond to me. So in the last session of this series, we are going to do or analyze the actual gas turbine cycle. So we have completed the ideal gas turbine cycle in all the possible respects, in all the way possible. We have seen its questions. So in the last session, we are going to see, what we are going to see about the actual gas turbine cycle, and we will conclude this series. Okay. Okay. So if there is any doubt, you can ask me, or we can end this session right now. So at the end also, I will like to request you to like and subscribe the GATE Academy. Okay. And do share it with your friends also, because this is a very useful series what we are doing, because this is a new addition to GATE syllabus. Very, very important. Okay. Very, very important to all of you. Okay. So please share it with your friends also, so that they can also get the benefit. You can send us your feedback. You can tell us if you like this video or not. You can tell us your suggestions, okay, in the comment section, as well as you can mail to us on the ID you can see on the screen. Okay, you can call us as well. Okay. Okay. So thank you very much. Thank you for watching the video. Do see the last session also. We are going to be live at 1 p.m. today. Okay, so in that we are going to see the actual gas turbine cycle. Okay. Okay. So thank you very much. We'll meet again in the last session of this series. Thank you.